So we was looking at motor basics, right? And we got through the DC motor. We looked at a shunt, a series, and a compound motor. This class, we're not going to talk about stepper motor and brushless motor. We'll get those later on. In fact, I need to take that out of y'all's PowerPoint. We know the parts of a DC motor. It consists of the armature, which is the rotating part. Some people call it the rotor, but technically it's called the armature. Then we have a field, which is mounted on, some people call it a stator because it's the stationary part of the motor. So the field does not move physically, but we can make the magnetic field move, and we're going to have to do that in AC. So DC, the south, north and south is stationary. What we're constantly changing is the field, the magnetic field going to the rotor, right? So we have that unit here. We call this a commutator. What it's basically doing is constantly switching the north and the south pole up here. And if this was south and that was north, the motor would do what? It would constantly spin, right? So we're letting the motor itself create what we call a shifting magnetic field. So motors, well, how does electrical motors operate? Well, they operate on the principle of repulsion and attraction of magnetic fields. At least one field's got to be electrical. And what happens, electromagnet, what advantage does an electromagnet have over a permanent magnet? We can turn it off and we can turn it on, and we can also shift it, right? You understand? So I can change the connection and actually make the north pole the south pole and the south pole the north pole. So that's basically what we're trying to do with the motor here. So we can control an electromagnet. We can't control a permanent magnet. Permanent magnets, you get what you got. The south pole will always be the south pole. The north pole will always be the north pole, right? You understand? An electromagnet, what can we do? We can turn it off. We can turn it on. We can control the strength of it, and we can also shift the poles. So this winding here might have been a north pole, but might have been a south pole. But when that same winding shifts up there, we might change it back to a north pole, right? You understand? Because we're doing this electric. So that's a big advantage that electromagnet has over permanent magnet. So we looked at a shunt motor. Everybody okay on a shunt motor? So shunt motors have really good speed regulation. They have okay. Then we have what we call a separately excited motor. We can change the armature, but by the way, when we change the armature voltage, we are changing the armature current, right? You understand that? So the more current you put in there, the stronger the field, right? You understand that? But how does the motor work? Well, the motor starts up. It has very, very, very low opposition in the armature. We put voltage across it. But as soon as the armature starts spinning, it starts cutting this field right here, and it induces the voltage back into the armature that we refer to as a counter EMF. And what that appears to us, it appears that the resistance of the armature is going up, which is what we wanted to do, right? We need a real strong current to start the motor. Why? We need a lot of torque to start the motor. Torque is proportional to current, right? How strong the field is. So why do we need a real lot of torque to start a motor? An object at rest wants to do what? So you got a motor, and we don't just use a motor to turn something. We use a motor to move things, right? You understand? So not only are you dealing with the motor being at rest, you're also dealing with the load that the motor's trying to move being at rest. But once something's in motion, and once you get it in motion, then you don't need that torque anymore, right? You understand? So what would we like the torque to do? We'd like the torque to do what? Start off real high, and then do what? Then drop to whatever's required to run the load. Everybody understand that? So what would happen if we was to look at a torque curve for a shunt motor? I don't know if that's in this PowerPoint or not. Then you'd see it goes like this, and then it drops off, and then it would kind of level off. And that's what a shunt motor would do. So a shunt motor is going to try to, and if it tries to slow down, the armature is going to try to slow down, which causes the counter EMF to go down, which has caused the current in the armature to go up, right? You understand, which causes the torque to go up, and it'll come up to the right speed. So one good thing about a shunt motor is some people call them constant speed motors. They'll run at the same speed. Whatever voltage you put on the armature, they'll run at that speed if you don't change the field. So these are what we call constant speed motors. They want to run at the same speed, right? If the motor tries to speed up, the counter EMF goes up, which causes the resistance in the armature to go up, which just causes the current to go down, produces less torque, which means the motor would slow back down until it's providing enough torque to turn the load. So these guys have really, really good speed characteristics. This guy, we can control both of them, so we can increase the torque by increasing the field. But if we increase the field current, then the speed of the motor goes down. But if we increase the field and increase the armature, the motor will run at the same speed, but at a higher torque. So the advantage of a separately excited motor is that we can control the torque and the speed. So if we wanted to produce more torque at the same speed, we could increase the voltage on the field and increase the voltage on the armature the same amount, which is pretty nice. So you just get more control, but the compound motor costs more than the shunt motor. And then we look at a permanent magnet motor. This is what you got on your car. Here you only got one option, is to control the speed by controlling the voltage you put on the armature. So the more voltage you put across the armature, it goes up, which causes the current to go up, which means the motor would try to create more torque. Well, what it would do is if it creates more torque, it's going to do what? It's going to run faster. If it runs faster, the counter EMF would eventually will knock it off, and that's where it'll stop at. So the main way we control the speed of a DC motor is by controlling the amount of current we put through the armature, which would be correct proportional to the voltage. So the more voltage you put across the armature, the current will try to go up. If the current goes up, the speed of the motor will go up. How fast will it go? Until the counter EMF and balances with the EMF applied to the armature, right? You understand that? These guys are what's the advantage of these guys? They're very cheap. Because we still have a wound rotor, but we no longer have a electromagnetic field. Does that make sense? Anytime I start adding copper, I start adding what? Copper. But we don't get as good core, we don't get a good speed with it. Now this is a series motor. What's the advantage of a series motor? Very slow speed, but great torque. These guys give us a lot of torque. We compared this with a hand drill, right? Most of your hand drills are series motors. So we said you hold them up in the air, and they run real fast. As soon as you put them in that piece of wood, what do? They slow down. But what happens is their torque's going up, right? And some of these drills now, guys, you got to be careful with them. They create so much torque, you can't hold on to them. If they get caught in the metal or something, sometimes as soon as you're going to break through the metal, it'll put a little, and it'll jerk that sucker right out of your hand. I got it's an AC, but it's a half inch, and it's got a handle on the side. You got to be careful with that thing. That thing will break your wrist. Of course, then we have a compound motor. This is these guys share the characteristics. So these guys have pretty good speed regulation, not as good as a shunt, right? You understand? But better than a series. It's got really good torque characteristics, not as good as series, but better than a shunt. So these guys are usually always electronically controlled. And then we have what we call a cumulative compound, which has higher torque characteristics, but less speed regulation. Then we have a differential compound, which has good speed regulation, but doesn't have really good torque. These are called compound motors. So how do we control the speed? Voltage increases on the armature. Voltage increases, speed increases. Voltage decreases, speed decreases. Normally used because if the speed control circuit fails, the motor will stop. Field, if we increase the voltage to the field, which increases the current, y'all understand that. Decreases the speed while torque increases. Voltage decreases, speed increases while torque decreases. Not normally used. And why? Because if your control circuit on a shunt, a compound, and a permanent magnet, well, we can't do it on a permanent magnet motor, but a shunt, a separately excited, and a compound motor, the motor could run away if you lose the field. So this is why normally we leave the field of roads alone. Are we okay? Yes, no? Reversing. The reverse electric connection going to the what? Armature and not the field. This is the normal way to reverse a DC motor, because if the reversing circuit fails, the motor will stop. We could reverse the electrical connection to the field and not the armature. Very seldom used, because a shunt, separately excited, or compound motor may overspeed if the shunt field connection is lost due to the failure of the reversing circuit. So the normal way of reversing a DC motor is to reverse the connection to the armature. Everybody okay? Of course, we're going to figure out how to do that with relays. Everybody okay? The motor will not reverse if you reverse both the armature and the field. It'll run whatever direction it was running at before. So what you got to do to reverse a motor is you got to change the orientation between the fields. And I wish we still had our DC motor in here. Before Mr. Sanders moved all the motor classes over to Birmingham, so we don't have a nice DC motor that I know of. I need to get one in here that has both a field. AC motors. We have single phase motors and we have three phase motors. And we're not going to look at the synchronous motors. We're not going to look at the wound rotor motors. These are special purpose motors. So we'll just look at this. So single phase motors, we have what we call a capacitive start, we have what we call a capacitive run, and we have a split phase motor and a shaded pole motor. We probably won't look at a shaded pole motor. I'll show you it, but we can't reverse those electrically. A shaded pole motor, the only way you can reverse it is mechanically. So we're looking for the motors that we can reverse electrically, right? Understand? So how many single phase motors do you have in your house? Or at your house? Some of them might be outside of you. How many you got a washing machine in your house? How many you got a dryer in your house? Right? You got like an ice maker in your house. Right? How many got an air conditioner in your house? Right? A heater in your house. But everybody, and all these use single phase motors. Right? Then we'll look at three phase motors. Industry primarily uses three phase motors. And commercial or residential uses a lot of single phase motors. So single phase motors, these are going to be what we call induction motors. What we mean by induction? What's induction? Everybody understand what we call mutual induction or induction? What's that? Nobody here knows? So if I put a coil of wire and I put current flow to it, it creates a magnetic field for it, right? You understand? If we put AC into that coil of wire, it creates a changing magnetic field that has motion. If we get two coils close together, it will induce the changing magnetic field in one will induce a voltage into the second. And that's what we call induction. So induction means you induce the voltage into a second thing from the first, right? And what do we need to do to induce a voltage magnetically? We have a magnetic field. Two, we gotta have what? Conductor. And three, we gotta have what? What we call relative motion, which means what? I can move the conductor through the magnetic field, right? Understand? Or I can leave the conductor stationary and move the magnetic field across the conductor. And what determines the amount? DC would be what? By the way, this is going to be on test sooner or later, and it's not going to be on the review. N3 would be the what? So AC creates a what? What does AC? So if I've got DC, I've got a magnetic field and I've got a conductor. But I gotta have what? Motion. DC don't have motion. So if I want to do it, I can spin it like the alternator on your car has a DC permanent magnet that's spinning, not permanent magnet, a DC electromagnet that's spinning. But it's spinning, right? You understand? So we create motion from your car, right? But I can take these two things, and this is the way transformer works. So transformers work off of what we call mutual induction. So we come over here, we have one coil that we call and some of y'all miss this, guys. Transformers, we don't call the coil input coils and output coils. We call them primary and secondary. That's the name of the coils. So some of y'all missed that on your chapter quiz. I need to show y'all some of those chapter quizzes, guys. I don't understand some of y'all's questions. Then we come over here and we bring a coil close to it. And then we couple them together with laminations. And what are laminations? Laminations are very thin plates, right, that are usually coated with some type of varnish. And what do those laminated plates prevent from happening? Prevents the eddy currents from combining into one big current and makes the core get very hot and get inefficient. So most of our transformers are at least 95% efficient. That means so, you know, I get 100 watts out, I might be putting 105 watts into the transformer. So transformers are going to get warm because they're not 100% efficient, right? You understand that, but they're pretty good. So that means if I can take a field and then I can make a conductor, then I can induce a voltage into that conductor, and that's the way induction motors work. So what we have on an induction motor is we have a stator, which is the field, the electromagnet, and then we have what we call a rotor, which is, it kind of works like the secondary of a transformer. Let me find this rotor over here. It's over here. So here's the stator, and here's the rotor. And you can't really see, yeah, you can see that. And I don't have my camera hooked up. So what we have is we have a rotor, and it's on two sides, and then we have these conductors that go from here to here to here to here. In fact, it's slanted, guys. And when I come over here and put a coil on that, it induces a voltage into that. These things are shorted on the outside. So basically, when you start an induction motor, it acts like a transformer with a shorted secondary, which means it's going to put a lot of current. It's going to create a very strong magnetic field, and it's going to create a lot of torque. But then the motor starts spinning. Well, the motor starts spinning, then what happens is, from an electrical point of view, the resistance of the armature, and we'll talk about that in a minute, actually starts increasing, which means the current in the armature in the rotor goes down, which means the torque goes down, right? And we'll talk about that in a minute, how that actually works. So single phase motors, the rotor current is provided by what? In induction, there is no brushes or slip rings. Requires an out of phase voltage to generated in a secondary winding called the what? Start line, to start. So what we gotta do is somehow, if I come over here, I've gotta make one of the phases shift, right? You understand that? Of course, we're gonna do that with this state. Starting torque is low compared to a three-phase motor. Easy to repair and maintain. It's less efficient than a three-phase motor. The power factor is pretty low. We like high power factor. Mostly used in domestic and small commercial applications. Normally reversed by changing the direction of the start line. Three-phase motor. Rotor current is produced by induction. No brushes or slip rings. Does not require a start winding. Has a really high starting torque. These guys are hard to repair and maintain because of the way the windings overlap each other. Has good starting torque. Starting torque efficiency is high. Power factor is high. Normally used in industrial applications. Normally reversed by swapping L1 and L3. So these are the basic characteristics of single phase and three phase. Three-phase motors are a lot more expensive because it's got three windings. They got a lot of copper in them, right? You understand that. Single-phase motors are very cheap for horsepower.
What kind of motor is in a ceiling fan?
Single-phase. How many phases do you have at your house? How many wires do you have coming from your down drive? Do you have two or do you have three? Huh? Two. Single-phase. Everything coming in your house is single phase. The only place you're going to run into industry three phase is in commercial applications or industrial applications. But you got a place like Burger King, they use a lot of fryers, a lot of energy, so their motors they're going to have three phase coming. US Steel runs three phase, but they also have single phase because we got a lot of devices that are not designed to run off three phase. Right? Like a fan. I don't think I've ever seen three-phase. I'm sure they're out there, but most of your fans are single-phase because they don't need a lot of torque, right?
What about the commercial air conditioner? What about the commercial air conditioner?
Commercial air conditioner will probably be a three-phase system. I'm not saying it will. The advantage we have with three-phase, guys, is we can get more. The formula for single phase is power. Of course, this would be VA is equal to V times I. For three phase, it's going to be equal to V times I of any phase times the square root of 3. So basically, if I can split my current over three phases, or my power over three phases, or the current. We'll talk about delta and Y. Now, Boyd is supposed to be teaching transformers. We'll learn a little bit about transformers. So we got two ways we can wire a transformer. We can wire it in what we call delta, or we can wire it in what we call Y. So what we do on a delta is the three phases would have exactly the same voltage, so the current would be divided by the square root of 3. So delta is used to transmit because it requires less current to send that power. And we're trying to get the current down. Why are we trying to get the current down for power being transmitted? Because every wire has a resistance. If you look at, to us it don't seem like much. We're using little tiny wires in DC, right? And we're using what, 22 gauge wire? 22 gauge wire has like 12.6 ohms per mile. So that means if we run a mile out there, that'd be 12.6 ohms, right? You understand? Okay, over a mile. But we're using this guy right here, so we're using maybe 6 inches, so we don't even have any equipment that can measure the resistance of that wire. But just think about it. If I've got 24 gauge wire and I try to send, and I've got a mile of it, and I try to send 1 amp, it's going to drop over 12 volts. Right? You understand that? Well, Alabama Power and TVA is not trying to send, they're trying to send thousands of amps, right? You understand? So if my wire has 1 ohm of resistance, it would drop 1,000 amps would be 1,000 volts per mile. But if I get half that current, right, you understand, then it's only going to drop half of that. So this is why Alabama Power is concerned with getting that voltage way up there. And then if I can actually reduce the current by the square root of 3, then that's best. And that's the advantage of Delta. So just about all power is sent using three-phase Delta. But the problem with Delta is we don't have a common connection, so we can't have a common on a Delta circuit. So Y, what we do on Y, we increase the voltage, right? You understand that on the output to get the power. And what's nice about a Y, but you don't reduce the current by the square root of it. So what's so nice about a Y is that it has a common connection. So now we can establish a ground, right? You understand that? We can establish a common. So your transformers for transmitting is usually wired in what we call Delta. And then your house in three-phase is usually done in Y. Industry uses both. They'll use Delta on extremely high powered three-phase devices. And then they'll use Y on just about everything else so we can set the time. So yeah, our house uses what? These guys, because we don't need a lot of power. We don't need horsepower. There's not even a 1 horsepower motor in your house anyway. All of them's going to be fractional horsepower motors, right? You understand? You get out in the industry, you're going to run in some big motors. The biggest motor that I knew about it, you guys tell, they could have a 3,000 horsepower motor out there running the blowers on the Q-box. So what we have to do on a single phase motor is create a phase shift. So we have 2 windings. We have a run winding that's across the line all the time, and then we have a start winding that we bring in. Now, once something's in motion, just the spinning of the rotor will create the phase shift that we need. So what they do is the start winding is going to be made with as little copper as they can possibly put in there, which means it's not very sturdy. It's not designed to stay across the power the whole time. So what they do is they have what we call a start winding. And what the start winding, and then on the motor it has a centrifugal switch. Where's my rotor at? Like I said, so this is the centrifugal switch right here. So what happens when the motor comes up to speed, these guys right here do what? They'll fly out. And when they fly out, they move that plateau down, and that'll cut out the start winding. There's a switch that's sitting on this thing right here. And then when it comes up to speed, it'll drop and drop out the start winding. That way, the start winding is not going to have a lot of copper in it, but it's going to create a phase shift. Y'all saw that, right? Remember almost the first of class, what did I do? I took that roll of wire, and I started doing what? I started winding it, and what did it create? It created a phase shift, right? You understand? So what we can do, we got 2 devices that can create a phase shift. We have capacitors. So capacitors create phase shifts, and inductors create phase shifts. I showed you an inductor. I didn't show you a capacitor. Capacitors are usually, they create a better phase shift than inductors. So what we do is we start this thing up, we put this line in here, we create a phase shift right here, and what the rotor does, it appears that the 2 things are rotating. And it causes the rotor to start spinning. But once the rotor starts spinning, what do they normally do? They kick that start winding out. So a capacitive motor basically has a what on it? A centrifugal switch. It has a capacitor and then a low induction start line. What's the capacitor in there for? So the start line, you can tell when the start circuit goes out because the motor will just sit there and hum because it don't have that shift. So when it does a north right here, it's going to do a south, and then when it switches, it's just going to sit there. But what happens is when this north starts going down, your start winding starts shifting a north over here, right, or a south over here, and it causes it to rotate. So in a single phase motor, if it just sits there and hums at you, it usually means either your centrifugal switch is screwed up or your start capacitor is gone out. And we see these things go out a lot in air conditioning units that are outside. which most people have their air conditioner outside, right? Because you're exposed to all that lighting and all that garbage out there. And these start capacitors will go out on them. And you call a repairman to come out there and they change the start capacitor out there. It costs them maybe $11. And then they charge you what? No, they charge you about $200 or $300. Yeah. Just change that capacitor. I had a swimming pool, and it sat there and hummed at me. What did I take for granted? And I didn't even check it, guys. You can check a big capacitor. I'll have to show y'all that. And you can actually see the capacitor charge up with an ohmmeter. So you can put it across there, and then you can see it charge up to overload. I didn't even check it out. I took for granted it was a capacitor. I went down to Whittington down here in Bethlehem, and they didn't have it, thank goodness. And I went back home, and I thought to myself, well, Rich, you didn't check this thing. And I checked the capacitor, and it was good. So what was wrong with my pool was that it was a pool, and the centrifugal switch had got corroded. So it wasn't making, so it was never closing, so it didn't pick up. So I cleaned that off, and the pump's still running somewhere. I don't know. I took my pool down. It was above ground pool. We do have another type of motor they called it a capacitive run motor. But what they do is they put better start windings in them, and then they leave one capacitor in all the time. So these motors always have a phase shift from the start winding and run winding, but it's not enough to really start it. So what they do is they have a start capacitor that they close in, and they still have a centrifugal switch. These guys cost more money because the start winding is bigger, but it's small. These motors are smaller per horsepower. Does that make sense? So if you're limited to the amount of space that you can mount that single phase motor in, then you would have to buy a capacitor run motor. And you can tell these, normally they put these capacitors on the side. Usually they mount on a lot of motors, they mount the capacitor on the side. So they have a pump on them. On the air conditioning system, the capacitors are outside, so they go bad so many times that they'll mount the capacitor outside. So the two brown windings that you see on the stator, you can see the two brown windings, that's your start capacitor. So on an HVA system, that capacitor is not going to be on the motor, it's going to be outside. And normally you can just pop the top and just change that thing out pretty fast. If it's got two humps on it, like this, then this is going to be a capacitive run motor. One of them's on there for starting and one of them's on there for running, right? You understand that? It uses both of them to start and only uses one to run. These guys have more horsepower for their physical size. So that's the advantage of these things.
So you can use both of those to start? So once it starts, what happens to the other one?
They switch it out with a centrifugal switch. Right here. Notice the start capacitor. So this would be a capacitive run motor. It's got a start. It's got a 1, so it basically creates a real good phase shift when the motor starts, and then it drops the phase shift also when the motor runs. These guys do have a better torque per watt, per side. Okay. You're not going to have any. A lot of your outside. I've got a what they call a combo unit. So I've got gas heat and electric. But they'll use dual capacitors. But one of them is used for your blower and one of them is used for your compressor. So they're still capacitive start motors. So don't get that confused. But you'll have to change out the whole capacitor when you do that. So you'll see it's got the one in your HVAC system outside will have 3 prongs set on it. One of them will be a common, and then you'll have 2 capacitors. Now you need to read the size or take that thing in there with you. I don't know of any place that sells these things commercially, locally. We have Whittington, which is a HVA system, but they don't sell to outside. They just sell to commercial people. Like you have to be in the business to do that. Luckily, we teach HVAC system down here, so these guys call and they'll call up there and say, I'm sending somebody up there to get a capacitor, and I go up there. But you can order them online, but you need to look at the can, and it'll have so many microfarads at so many volts, and that's what you need to look at in order. If you put the wrong capacitor in there, it might not start, or it might burn up your coil because you have too much ratio. So the size capacitor depends on the induction of this coil right here. So and that depends on the manufacturer. So on the side of the capacitor, it have so many microfarads or whatever on the side of it. So speed control the speed of AC motor. It's not normal. So speed is not normally controlled with voltage. If voltage is lowered, both the speed and torque decreases. If voltage is increased above the rated voltage, torque increases, but speed does not. Speed can be changed by changing the number of poles. So the formula for the speed of the motor is this is the field speed. This is not the rotor speed. Is RPMs of 120 times frequency divided by the number of poles. The speed of the motor is going to be minus what we call slip. So we can control the speed of the motor. It looks like we can control it two different ways, right? What two different ways can we control it?
You can change by changing the number of poles. And you change by proportionally changing the frequency.
It looks like it, though. We can't do that. It looks like it. It's like the frequency goes up, the speed of the motor goes up. The frequency goes down, the speed of the motor goes down. That's what it would be. They call these drives, they call them variable frequency drives, but you just can't change it. Normally we change it by changing the number of poles. And so if you got a ceiling fan, it's usually a 3-speed fan. You go over and you click it, thing. What are you doing? Every time you click it, you're doing what? Changing the number of poles. You're not changing Alabama Power 60 cycle. Or for one thing, I can't change Alabama Power's frequency, right? Don't understand that. So Alabama Power runs a frequency of what? 60 hertz. In fact, that's the entire continental, our whole continent here uses 60 cycles. All the way up through Canada, all the way down through South America, they use 60 cycles. But when we get over in Europe, they start changing things around. Over in Europe, over in that continent, usually they use 50 cycles, and then you have some countries that uses mishmashes too. So if we're going to change the number of frequencies of the AC motor, we're going to have to do it electronically, right? So that's why this motor right here, this is a three-speed motor, and it's got all those windings coming out of it. It's got all those wires coming out, right? The two brown ones are for your start capacitor. And then you have a red one, you have a yellow one, you have a blue one, right? You understand that? Well, what we're doing is we're bringing power on each one of those to change the number of poles. If the number of poles goes up, the speed of the motor goes down. So the fastest a motor would run, we've got to have at least two poles, right? We've got to have at least a north and a south, and a south and a north. So that would be the fastest an AC motor would run. And so 120. This would be, the formula is 60, because we use 60 cycle over here, right? Over here it would be 50. But 60 times the number of pole pairs, because the motor makes one revolution when it goes through a pair, it makes one motion when it goes through a pair of poles. So if I've got two of them, that means it would make one complete revolution. Right, you understand? But that would be for two pole pairs, and we're running at 60 cycles, right? You understand? So what we're doing is they don't call it a 2-pair pole motor. They don't say it a 3-pair pole motor. They say it's a 2-pole motor, a 3-pole motor. That's the way they're rated. So what we do is we say, instead of using 60, we say 120 times the frequency divided by the number of poles. And that's the way motors are rated. So the fastest an AC motor would run over here would be what? 2-pole motor would run what? 2-pole motor, 120 times the frequency, right? 60 cycles. I'm sorry. We use 60 because it's in seconds, right? frequency over here, we use 60. So 120, I got that off. This is because we're doing revolutions per minute, right? You understand? How many seconds in a minute? 60, right? So that's how fast it would be, 60. And then that would be divided by the number of pole pairs. So we're doing the number of poles, so that's why we use 120. That makes any sense. So the fastest an AC motor would run over here would be 3,600 revolutions per minute, but it can never run that fast. Anybody know why? So we start off with a rotor sitting in there. We throw power on our stator, and it's doing 60 cycles per second. So we get a bunch of cutting. The rotor starts turning. Well, what's happening is the rotor's catching up with the field, right? You understand? So if the rotor's running at 5 RPMs, and then then it would only get 55 RPMs instead of 60, right? You understand? So what happens is the speed of the motor goes up. What changes? The relative motion between the stator field and the field being induced in the rotor. And the motor's always got to produce torque. So that means an AC motor will never run at the field speed. So if we got a 2-pole motor, the field is moving at 3,600 revolutions per minute. But the rotor cannot run at 3,600 revolutions per minute because we would have no difference between the rotor field and the stator field, and we'd have the relative motion. So induction motors will always have slip. So that's a 4-pole motor. We're using a 4-pole motor, right? You understand that? So the field speed would be what? Will be 1,800 RPM, because I've doubled the number of poles. But if we look at the speed of the motor, it says at 60 cycles, it's going to run at 60 cycles, half a fourth horsepower. This guy's going to run at 17. So an induction motor, the rotor will never run at the same speed as the field. Because if it did, we would lose what? We'd lose our relative motion. Everybody understand that? But as the speed of the motor comes up, the relative motion goes down, the amount of voltage being induced to the rotor goes down, which causes the current to go down, right? You understand that? So it looks like as the speed goes up, I had somebody teach this, that as the speed goes up, the resistance of the armature goes up. It's not the resistance of the armature going up, it's the speed of the voltage. I mean, it's the speed of the revolution that's going down, right? You understand that? So that's the way these guys work. So this is the speed. The speed would be the RPM, and then minus the slip. So that guy got over there got a 75 RPM slip. Control the speed with frequency and voltage. Due to something called inductive reaction, the opposition of the AC motor changes with the frequency applied to so the formula is X is equal to 2 pi FL. We understand this. Is that if the frequency goes up, the X of L of the motor goes up. So it says X of L is opposite. If the frequency of the AC motor changes, its opposition to the AC changes. If the frequency goes up, the opposition goes up, the motor's torque would go down, so the motor could actually stall. If frequency goes down, opposition goes down, and torque goes up. Now we're going to create more torque that's required to run the load, and the motor could overspeed. To control the speed without changing the torque requires both the what? Voltage and the frequency to be changed, proportional. So when you program a variable frequency drive, which is a misnomer, I like to call them variable speed drives. Most people call them variable frequency drives, so they think they're changing the voltage, the frequency on them. But you just can't change the frequency to control the speed of an AC motor. You got to change what? Voltage and frequency. So when you program these things, that's two things that's very important. To enter the right voltage, right? You understand that. And also to enter the right frequency. They call it hertz per volt. So basically it maintains this.
Your program, don't they use it for?
Huh? What's that?
Your program, don't like
Not the manual, the motor. You get this information off the nameplate of the motor. Yeah. So that's some information we need to understand is that motor gives you that nameplate gives you a certain amount of things. It's going to give you the voltage. It's going to give you the horsepower that it's going to develop if you put that voltage across it, right? And it's going to give you the frequency that the motor is designed to run at. Some motors will run on 50 hertz, but what they're going to do there is they're going to change the speed, right? You understand that? So what you do is you look at that nameplate and you say, okay, I'm going to run, you have to put that in there. You put the voltage the motor is supposed to run at and what the frequency is supposed to run at. And then you take that and enter that into this, and it's called a volts per hertz. As long as you can maintain this right here, you can control the speed of the AC motor. But you don't have to calculate it because the variable speed drive does that for you. But they don't call them variable speed drives, they call them variable frequency drives, VFDs. And this is done electronically. So what they do is they bring the AC in and they turn it into DC right off the bat. They turn it into a plus and minus DC. And what advantage does DC have over AC?
You control
electronically. So we got function generators y'all play around when you get into AC. You bring in 60 cycle Alabama power and you can adjust the frequency all the way up to megahertz because you're doing it what? Electronically. So we can take DC, convert it to a plus and minus AC, a plus and minus DC, and then we can get whatever the heck we want out of it electronically. So we do that. We don't ever run the motor above its rated frequency. And you have to, get the thing running. So but what's nice about an AC motor, variable speed drive is you can set an acceleration on that thing. So it'll actually do, it'll bring that thing up to speed instead of just trying to start it up with full power. So variable speed drives are really neat. Single phase motor, these are more expensive. We have what we call a split phase motor. These are more expensive than a single phase motor, capacitive motor. Characteristics more expensive than a split phase motor. Starting torque is between 200 to 400% of full load current. Lower starting currents, 400 to 570% of full load current. These are the workhorses of general purpose industrial motors. These passive. These are all over. Showed y'all that guy, right? Then we have what we call a split phase motor, less expensive than capacitor motors. Low horsepower, very low starting torque, 100 to 175% of rated load. High starting current, 700 to 1,000% of full load current. Single phase. Y'all know what the full load current is. This is a very important thing. This is, if you look at the nameplate, this is amps. So what is the full load current? When it's running at its rated voltage, at its rated horsepower, at its rated frequency. That's how much the motor should pull. If you lower the frequency, the motor's probably going to have to pull more current to produce the same horsepower, right? You understand that? So that's what it's on the nameplate. So if you look at the nameplate, it's not called full load current. It's called amps. And that's how much current the motor should pull if you're doing what? Running at its rated voltage, at its rated horsepower, and at its rated frequency. So this guy said right here, it could pull 700 to 1,000 times more just to get this motor started under load. Under load, not by itself, right? It's got fairly low. We'll see this guy's used on a lot of compressors. These guys are used on a lot of fans. These things on a lot of fans. Something that don't require, so fans are weird. Most things require a lot of starting torque. Fans, the starting torque is low and the run torque is high. because it gets its torque from trying to move the air, right? So these guys are used a lot of fans, a lot of. So grinders, so your grinder don't come up to speed real fast. Anybody got a grinder? I got one. That's one of my units I have at the house. It's paid for itself quite a few times. Small fans and blowers. So here we get the phase shift out of nothing but induction. But we still have a centrifugal switching. Are we okay? Yes, no. How do we reverse this thing? Is that them here?
You said down.
That's the DC mode. So here we have no connection to, in fact, here they don't call them armature. So on an AC motor, the rotating part is called the rotor. And the stationary field is called a stator. And then of course, then you've got to understand when we talk about the parts of a DC motor, we say, okay, it's got the armature, it's got the commutator, it's got brushes, and it's got a field. And what do we forget? We forget about the frame. You got to understand every motor's got a frame, right? And what's the frame? That's what the motor's mounted in, right? Have you ever seen a motor that's not mounted in a frame? You know, they had some motors out of US Steel with frameless motors. They had two things that held the bearings on there, but you could see the whole motor. It was really neat. These were big old motors. They were over in the sheet man. Big old motors. They actually was probably as high as this, and they went down inside the floor too. So these were huge motors. That was the only big frameless motor that I ever seen. And we get into framed motors because it makes them safer, right? It gives them more mechanical support. So all this would be a frame. And of course the frame would have the bearings in there. What's the bearings list is? It's a function of a bearing. Nobody knows what bearing. Yeah. It allows something that's in a rotary motion to be attached to something that don't move, right? You understand? With very, very little friction. We have all different types of bearings, huh? Yeah. So you're stationary and the fidget spinner is what? Spinning. So what it does, it allows something to do what? It's spinning to be attached to something that's what? Stationary, that's not spinning. With very little friction. That's so what bearings are. Yeah, we got some fidget spinners that you could get over 3 minutes on them. Very, very little friction. So you had fidget spinners? My youngest granddaughter collected them things. She was dead. I don't know how many. So what we do to reverse these things is we got to reverse one of the fields. Since the rotor is induced, these are the two fields that we're dealing with, right? We got to change the relationship between these two fields. Which one do you think we do the most often? Start winding. The start winding is the industry standard for reversing the single phase motor. If you can. A lot of your single phase motors, they don't make the windings available. Like that guy right there, we don't have control of the winding. So this motor would run in one direction. It's either going to run clockwise or going to run counterclockwise. So that's something you got to think about when you buy a motor for your HVAC system, your air conditioning system. Which direction is it supposed to run? Looking at it from the engine. Then some single phase motors have a plate on them, and you can open up the plate and look in there, and you can get to the start winding and run one. So what we do is we swap the connections. The standard way is to swap the connections on the start winding. Three-phase motors. What's nice about three-phase motors is that y'all understand three-phase. we've got is we've got 3 conductors, and they're generating a voltage that is 120 electrical degrees apart. If I can draw this okay. So this would be 120 degrees. So the other one would look like this. And of course it would come down here and go up, and this would keep going. And then the other one would be what? It would be 120 electrical degrees out of phase with this one. I think I can do this. It don't look good. I think I got a picture somewhere. So what happens is that if we look at this, while one's building up, while one's dropping down, the other one's building up. While one's dropping down, the other one's building up. And what this does is we put these things up, we put our coils 120, or electrical degrees apart, not mechanical degrees apart. And what this does is it generates a rotating field that moves around the outside. And of course, what's going to happen? The rotor's going to move with it. Of course, the rotor can't move at the same speed. It's going to have a little slip in there, so it keeps it up. So what's nice about a 3-phase motor, number one, is that they don't require start light. Yeah. Because the phase actually does what? I don't think I've got this in this PowerPoint, which I should. I should have put that in this thing. See if I can bring up another PowerPoint real quick. I should bring this animation into this. This is just looking at it at a time. So green phase, blue phase, yellow phase, and this black right here is power being created by the two. So you can see as it moves, the power automatically does what? Moves around the outside. So what we do with a 3-phase motor, we automatically create a rotating magnetic field in the state. This is showing the angles, how it builds up on these sides. It's pretty amazing. So the red field plots the polarity to this. But the maximum power always occurs where all 3 of them kind of cross. Now, how would I change this direction? Well, I got to make the power field move in the opposite direction. But this is 3-phase right here. I need to bring this into this PowerPoint.
So you said you can make it opposite way?
Yeah.
And you said how you do it?
So if we come up here and just call the phases, and normally when we talk about this, we call the phases what? We call it, normally when I didn't want to do that. So if we call the phases A phase, B phase, C phase, then right now we'd be doing like this, A, B, C, ABC, ABC, Rich. Yeah. So let's say we start off with ABC, ABC, ABC. You understand what I'm doing? ABC, BC, ABC, ABC. Now, what we can do is we swap any two leads. So let's swap C and A. So I'd start off C, B, A, C, B, A, C, B, A. Can you see what just happened? So now instead of going ABC, 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 it's going like CBA, 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 and the motor, the field would be moving in the opposite direction. So what we can do to reverse a three-phase motor is to reverse any two phases. I could have picked any one of them. I picked the industry standard. So the industry standard is to reverse C and A, or what we say. Of course, we don't see it from that point of view. We see it L1, L2, and L3. So the normal way to reverse a three-phase motor is to reverse these two right here. L1, L3. That's the industry standard. And what we want to do is we want to do things according to the industry standard. So that means the next person that comes in there don't have to figure out what we did, right? You understand? And get themselves hurt. So this is the industry standard to reverse L1 and L2. So we could do that. L1, it works better with ABC, but it would come up and do exactly the same thing. I'll bring this into our PowerPoint. I thought it was in there, but I keep going back to the same one. Yep, with that one. This is it right here, right? No. This is it. So we have two ways we can wire this thing. We can wire it in what we call Y. And you see why it's got the term Y, right? That's just the way it's drawn. When you see this thing's wired up, it's going to be all weird. And what we do is we have what we call a dual voltage motor. So a dual voltage motor means we can wire it for a high voltage or we can wire it for a low voltage. But you have to wire it. Because you can screw this thing up if you put a 440 motor on a 240 circuit, right? You understand that, or 220 circuit, or vice versa. So we rewire the motor. Now what's the advantage of having a dual voltage motor? A lot of the industry uses a lot of this.
No problem.
If this is a 5 horsepower motor, guys, it's a 5 horsepower motor. If I wire it one way, I better not get more than 5 horsepower. If I wire it for low voltage, I'm going to get 5 horsepower, right? You understand that? If I wire it for high voltage and I put it on low voltage, you're going to burn the motor up because the motor can't even create enough starting torque. If you wire it for low voltage and put it on high voltage, you're going to burn it up because it's trying to produce 4 times more power than what it's supposed to. So a transformer, and these are basically what these are. These are transformers, but the secondary is in motion, right? You understand that? So what advantage does high voltage have over low voltage? I'll put this on test too, and not put it on the review. We've talked about this over and over. What advantage does high voltage have over low voltage? Takes less current to produce that horsepower. So if I've got a 440 5 horsepower motor, it's going to pull so much. If I've got 120, if I got a 240 5 horsepower motor, it's going to require more current. I have to wire it for 240, right? Y'all understand if it's a dual voltage motor. So industry uses a lot of dual voltage motor. Now what they want to do is if high voltage is available, by George, they're going to wire it for what? High voltage. If high voltage is not available, then all they got is low voltage, and they're going to wire it for low voltage. But what it does, it gives us one motor that I can keep as a spare that I have the ability to run on what? Wire for high voltage or low voltage. So about how many watts would a 5 horsepower motor take? How many watts? About how many watts would it pull of real power? What's the conversion? How'd you come up with that? Yeah, there you go. So what did we come up and get? 3730. So if I wired that thing for 240, this would be I is equal to P over V. How much current would it take? Huh? 15.5, right? And of course 440 would take half that, 7 amps. 7.25 amps. 7.75. So this is what we do. So to wire this thing for high voltage, what I would do is I would hook these in series because high voltage requires less current, right? You understand? So we'd hook them in series. It's just like when we're doing high voltage on a transformer, very similar. So what we have on Y, guys, is your 3 phases has a common spot. And then if I bring voltage in, so if I bring in 240, then this right here is going to see 240 divided by the square root of 3, 1.73, which would be roughly 120, I think. So what would I do to wire it for low voltage? Well, low voltage is going to require more current. So what do we do on a dual voltage transformer for low voltage when we wire it for low voltage? So our transformer, we could take 440 and get 120 out of it, or we could take 220 and get pretty close to 120 out of it. Which one's going to require more current in the primary? This guy right here, right? You understand that? So here we wire them in series. Here we wire them in parallel, right? You understand? So here for high voltage, we wired them in what? Series, right? So if we wire it for low voltage, we have to wire it for parallel. So these are T. So this is what it's telling us. It says to run at high voltage, then I should have T4 jump to T7. I got T4 jump to T7. See it? It says I should have what? High voltage, I'm sorry. We should have T5 jump to T8. I have T5 jump to what? T8. It says I should have T6 jump to T9. I do. And it says my power should apply up here. So it says I should bring L1 relative to what your plan is. I should bring L1 and connect it right there. See, L1 to what? T1. L2 to what? L2 to T2. And L3 to T3. That make sense? Now to wire it for low voltage, we've got one Y already here. We've got this Y right here. So what I've got to do is create a Y right up here. So what I would do is I would take these 3 and connect them together. Right? You understand? And then I would take this one and connect it there. I would take this one and connect it there. I would take this one and connect it there. So let's see if that's right. So I should have low voltage. I should have 4, 5, and 6 connected together. 4, 5, and 6 connected together. I should have what? Oops, sorry. I should have L1 going to 1 and 7. I got L1 going to 1 and 7. I should have L2 going to 2 and 8. I'd have L2 going to 2 and 8. And I should have L3 going to 3 and 9. I got L3 going to 3 and 9. So what we've done is we rewired the motor, right? Y'all understand that? Okay. What would happen to the horsepower? Would the horsepower go up, or the horsepower go down, or will the horsepower stay the same? Stay the same. Good. Right? You understand that? It stay the same. So what we do on a dual voltage motor, and where are you going to find this information at? On the nameplate. If the nameplate is still there. There's a book. There's a procedure in your textbook, by the way. I'll have to find it for you, that tells you how to identify the leads on a 9-lead motor. So we call this a 9-lead motor, right? You understand that? Because it's got 9 wires coming out of it. And you do what? Well, not coming out of it. Normally they have it on a big plate on the side of the motor or on the back of the motor. They brought ours out. So if we look at our motor, it's got 1, 2, 3, 4, 5, 6, 7, 8. And that would be these, coming out of it, right? Everybody okay? Yes or no? This is a delta motor. Now, if it's a delta motor or if it's a Y motor, it makes no difference. A 5 horsepower motor is a 5 horsepower motor. So a delta motor or Y motor is basically transparent. You have no idea what it is. All you know is a 3-phase motor. And then what you're going to do, if you got a dual voltage motor, is you're going to look at the nameplate and it tells you how to wire it for what? High voltage and low voltage. So this is the way, right here, this is a delta motor. Oh no, this is a 12-lead. And we don't have any delta motors in here. All our motors are Y motors. I'll get the wiring diagram out to you. I don't see it in the PowerPoint. But what you would do is you would delta motor. So a 9-lead motor is what we call a dual voltage motor. Now the problem with motors is that, let's say I got a big old horsepower motor, 200 horsepower motor, and I start that motor up. About how many horsepower might develop for us? Well, we'll look this up. What's rule of thumb? 6 to 8 times, right? Understand? So that means a 200 horsepower motor, you put that thing across the line, that sucker could try to generate 1,200 horsepower or 1,600 horsepower. 1,600 horsepower could tear the gearbox up. It could tear things up, right? You understand that? So what they did for a while was that they did what they call reduced voltage starters, where they would come in there, and when you started the motor, they would put less voltage on the motor. And that means if you put less voltage on the motor, it would create less torque. So a lot of your big motors, we don't want to put those things across the line, because those suckers, when you start them up, they're going to pull a lot of current, but they're going to create a lot of torque. I've seen motors strip gearboxes out before. Just trying to do what? Just trying to get them started. And then you turn all that horsepower loose. So these big horsepower motors, we usually try to do one of two things. We try to, so what you can do on a variable frequency drive is you can put a ramp up there. You can say, okay, I want this thing to accelerate from 0 all the way up to 1,700 RPM at a certain slant. And what it does, it deliberately reduces the torque of the motor when you do what? When you start it up. Or we can run it through a bank of resistors, and then put resistors in series with it to start it up, which would drop some of the voltage when we try to pull all that current, which would put less voltage across the motor wouldn't be able to create all that torque. And then it wouldn't tear up the load. So we did that for years. We had that big OAC motors that we would put them across what they call they would call it what did they call it? What did I say a while ago? Or we could come up with a method. So what happens when we have a Y winding? When you have a Y winding, whatever voltage you bring in, the coil that goes to the motor sees that divided by the square root of 3. So 240 divided by 1.73 would give me what?
Turn 38.
Really? Maybe it's 220. Yeah, that's what. But that's okay. It's okay. So if we had a motor, now when we get up to delta, the voltage across the windings are the same. So that means if I come over here and put 240 here, then I would have 240 across this when I measure it, right? So what delta does to get the horsepower, it would be I divided by the square root of 3. So delta requires less current to produce the horsepower, right? You understand? Y requires more voltage to produce it. So if we had a motor that we could start up at Y to reduce the voltage to the winding, even though the voltage out here does not change, and then we switch it over to delta when it came up to speed, then that would be the ideal motor we would have instead of using an external reduced voltage starter. That's the term. So we're not going to look at how to wire this. So we have what we call a 12 lead motor. So a 12 lead motor we could wire for what? High voltage Y start, high voltage delta run, or low voltage delta start, low voltage delta. And how do we switch it between those? How would you think we would switch it between electrically? We switch it with what? Relays. Very complicated. Oh, it's not. He's playing on his phone. You already know all this? You come here to teach it for me? Okay. We'll see how you do on test, right? So how do we swap these things? And that's what we're important. That's what we're going to look at now as soon as we get back off the break. Is how do we reverse these things? So how do we reverse a single phase motor? What's the industry standard for reversing a single phase motor? Single phase motor. Good. Start the nation on start. DC motor. Armature. Three phase motor. Okay. All right. I'll take a break. All right, Chris, I'll get you in a minute.